Hello, have you ever had a class about artificial vision? Not yet? So, enjoy that this class is special for you.
The world will depend on young people like you, people who will invent the next generation of computers.
Hello everyone, welcome to a class about artificial vision. These systems is used to check the quality of parts, workpieces in the assembling lines. So why I choose this subject? Because in Mecatrônica competition in WorldSkills Kazan 2019, this was the system. Sorry, this was the system that was assembled there, and one of station used a vision sensor. So this vision sensor is responsible for check the workpieces. This is the workpieces, transparent, black, silver, and red, and a cover. So the system, the vision system, is responsible for check the whole direction of the parts, roll up and roll upside down here and up like this, and a presence of RFID tag in the parts. So this situation, without RFID tag, this workpiece must put in another way, in another slide, and this situation is good for the production. So let's start talking about the image. What's an image for you? So the image is from the Latin imago, that means visual representation of an object, and in Greek is called eidos. In the etymological root comes from the term idea or aid. Idea is a projection in the mind. It would be a projection in our mind about something. Idea of the image, of real image. In broad sense, an image consists of any visual form of expression of an idea. So in the visual systems, the images is an expression of an idea. Okay? So the real images are in 3 dimensions, in 3D dimensions. Okay? And the machines that like cameras or cell phones take the image, take the photo, and change the real image in a 2-dimensional image, like this. This is a gold house in Japan. This is the example. So from 2-dimensional image start the digital processing. The digital processing have 3 steps: sampling, quantization, and codification. And this process named discretization process. This is the name of these 3 steps. So what's this discretization? Discretization, it's the conversion of the image from continuous mode, this is a continuous mode, into a discrete representation, through points. So discrete image in several points. So each point there is x and y position, and these points named pixels. So let's talk about sampling. When scanned, the image takes on a dimension size in pixels, and you can know the size of the sample from the ratio between the number of pixels obtained and the length of the actual image. So this is called spatial resolution. and is measured in DPI or dots per inch. So here we have two examples, one image with a poor spatial resolution, and this is more good spatial resolution, more pixels per or more dots per inch. Of course, more high resolution is better for the image, but we need more processing capability and more storage capability. So, pixel. What's a pixel? A pixel is the smallest unit of a digital image. This is the minimal point. The word pixel is the agglutination of two words, picture and element. So one pixel is characterized by the location in the image, X and Y position, and the color intensity of value Z. Color intensity. What's the color intensity? The intensity of color is the next step named quantization. Quantization is a conversion of each point in the sample into an intensity value. But what measure of this intensity? How measure this intensity? 1, 10, 100, 1000? How many? So the quantization use a scale, a standard scale, and we have two standard scale. The first standard scale is gray scale or shades of gray. So let's take some points of this picture, and we can see this point is this more 47 number is more dark, and this point is this point. Okay, more more white, the number is more high. So the scale, we can use a lot of standards of scale, but I know this standard is around 200, and this scale have 80 bits of resolution. So 8 bits, the number is 0 to 255. So sorry, and this is important. Here we have a standard that 0 means black, total black, and 255 means total white. Okay, this is a standard in this scale. So another standard is RGB, red, green, blue. If that example is color example, something like that, we have 3 bands. This scale is named multi-band. 3 bands, of course. One band is red, another is green, and another is blue. So, and the data is 3 of 8 bits, totally 24 bits of data for each pixel. So, and the last step is codification. Codification is a set of data representative of an image, and this can be transformed into files. A digital image is described by an array of pixels, value, and color intensity. So, and this array you can transform in files to use in another processing steps. So the next step is digital processing. What's a digital processing? It's an extraction of important characteristics from the image that help in understanding the image and make intelligent decisions. For example, here we have an image of grayscale, and after digital processing, we have two types of images. For example, in binary form, and black and totally black or totally white, and edge form, for example. So now I will explain two tools to get this kind of image: binary image and edge image. Let's go. So it's important to use these two tools. Is use the histogram. The first point is the histogram. What's the histogram? The histogram is a bar graph that indicates the number or a percentage of pixels that the image has at a given level of gray or color. So, for example, here we have an image and the histogram. Let's see, for example, here is a white, totally white, and probably okay, how many pixels? 5,000 pixels is totally white. Probably these pixels and this is totally white. Okay, totally black we don't have. Totally black we don't have. And what more? So looking the image, the big part of the image is more white than black. So we can look this in the histogram. The more quantity of pixels is more from this side, more white than black. So the histogram provides an indication of image quality in terms of contrast and light intensity. So in the middle of the histogram we have midtones. In the left side we have the shadows, more dark, and in the right side the highlights, or it means more white. So if we are using a photograph machine and the time of length is under exposure, for example, the histogram is we will see the histogram like that, the pixels in the left side. If the time of length is overexposure, the pixels will be like that in the right side. And if you have a perfect time of exposure of the light, you have the histogram like that. It means all of grayscale or all of colors it's possible to see in the image. And in our image in the camera, we can see the histogram in the camera. Okay, this is example. This is the histogram inside the camera of this image. Okay, look how several pixels in several tones of color, and this is good. So here we have example of an image that is too dark and is no good. And in another point, this is an example of an image that was too lightning, too shine. And here is a good example. Look, the histogram have all of positions of colors. So another example here in grayscale, a perfect image, and here a perfect color image. So this is the best way. So, and the first technique that we will use, namely thresholding. The thresholding is a technique used for object recognition and interpretation through image segmentation. So let's have a segmentation of the image in 2, 3, or several parts. The process is based in the difference in gray levels that make up the different objects in an image. So, for example, here we have an image of our car, for example, and what we have recognition in this image, the letters and the numbers. So to obtain this image, the threshold technique can help us. So, for example, this is the original image. This is a rock, and we have the histogram. So, look in this histogram, we have one part with high level, probably the white side, the ground, and here middle tones. Probably the rock is the middle tones. So this is named a bimodal histogram, two groups of pixels. And here we have the threshold, and all of pixels from this point to the right side will be white, and all pixels from the threshold to left side will be 0, will be dark. And the result, this is the result. And this image, this kind of image named threshold image or binary image. Why binary? So why binary? Because we have white or dark on only this kind of pixels. And here we have a segmentation between object and background. So you can see object and background. Okay, so for the image that the histogram is bimodal, like the last example, the ideal threshold value can be obtained from the algorithm proposed by Otsu in 1975. Otsu proposed a histogram that take the pixels of the histogram and propose a balance. Check automatically, an algorithm that checks automatically the number of pixels in the right side and in the left side of the threshold. And the ideal point is when this balance is in balance. When these levels of left and right is in balance, this is the ideal point that Otsu proposed. So another example of thresholding. Now we have a multi-level threshold. Use this trimodal histogram. So probably these pixels is the background. This middle pixels is object A, and this object B. So this is an example of RM of the brain. magnetic resonance of the brain, and in the brain we need to the doctor wants to check the different structures: liquor, gray substance, and white substance. And to separate these images in three images, we can use a different level of thresholds, because the liquor is in this position of gray level, gray substance in this position, and white substance in this position. And less than threshold 1, less here in this point, we have a lot of pixels, and this pixels is out of our range, because probably this is the background, the black background here, for example, and this is what we don't want. So let's check. This is the histogram. They use 39 here, 85 here, and 151 here. And the result, this is the result. This is the liquor, this is the gray substance, and this is the white substance. And now the doctor can verify, can analyze each structure separated. So the second technique is named Conci technique, was developed by John F. Conci in 1986 in his article Computational Approach to Edge Detection. Take a look. Edge detection, this is the idea here. The edge detection of objects, check the variation in color intensity. Variation in color intensity. When we have a sudden variation, probably we have an edge. So this is the binary image. Check with, for example, we are right here. Okay, here this is white and this is black. Here we have a sudden variation, and probably here we have a edge, and we stay a point in this position, and the result is this the result, the edge image using the Conci technique. So okay, using the threshold technique, we can have a binary image and have the area of part. And using the technique, the Conci technique, we have the edge image, and the edge image, if I add all pixels, we have a perimeter. So if we have area, we can compare area, and if we have the perimeter, we can compare the perimeter. If you can compare area and perimeter, we can have a quality inspection. And this is the more basic techniques to have the quality inspection in the visual machines. So why this? The system, artificial vision system, can use it to inspection of dimensions, to use in a models, to use in a classification, and so on. Some examples monitoring the level, the field level, monitoring the position and rotation of the parts, to have orientation, to use in a robot, for example. The camera check the orientation and the position, inform the robot, and the robot take the part correctly. So check the inspection of labeling and printing of the cups, and reading the bar, the 1D code, the codes, the 1D codes, for example. Thanks for your attention, and see you in next videos. I will record another video about vision and use the other techniques, the other tools. And subscribe the channel, leave your like, and see you. Bye bye.